as well. Be able to see them today, I think. And also, let me see here. We're going to wrap up the design today. So I'm going to leave a new homework to Thursday, and we have class tomorrow. And we will go through the one-way slab design, continuous design as well. And we'll go through the ACI coefficient, moment coefficient. And so you should be ready to do homework tomorrow. And in addition to the regular content we have Thursday, which is tomorrow, we're going to add a few examples from the past year's exams on shear and also one-way slab design, particularly on this coefficient, moment coefficient distribution things tomorrow. Again, Austin, if you haven't heard, I am on leave actually for the rest of the semester due to medical reasons. So unfortunately, I have to continue this class online in the summer, but unfortunately, the rest of the class will still be online. But if you need anything, talk to me or anything like that, we can arrange one-on-one meetings online and we can try to resolve it. Or if you have any concern, just send me an email, we can deal with that. All right, apologize for that, it's just unforeseen. Hopefully I can get back to the teaching. It's most likely going to be fine. Anyway, so enough of my personal issues. Let's continue the one design where we left off last time. Okay, so let me share the screen so people to see the content here. Give me 1 second. Hopefully this time the technology doesn't happen again. We're here. All right, you guys see it? Anything? Do you see it? Screen on?
Yes.
Yeah.
Good deal. Thank you so much. So one-way slab, right? So first thing, one-way slab, let's recap. There are two directions in the one-way slab. One is longitudinal direction and the other is transverse direction. And as you know that we are calling the shorter span length as a longitudinal direction. Okay, and that is where the bending moment exerted along. That is where the bending moment exerted along. Now the other long direction, which is actually called transverse. Okay, this is longer span, but we call it transverse span because that span, we don't care about moment because there's no moment essentially for one-way slab, very small amount. For the other direction, we mainly consider the temperature and shrinkage for the reinforcement design. Okay. First thing, when you have a one-way slab in the exam as well, you have to make sure that is a one-way slab. So how do you ensure that is a one-way slab? You use a ratio between the longer span and the shorter span and make sure that is bigger than 2. So when the ratio is bigger than 2, that means that you have a one-way slab. Okay. Now also to show you that the key difference between a one-way slab and two-way slab is a moment distribution, right? In a one-way slab, we only see moment in one direction, which is along the longitudinal direction. But in the two-way slab, the moment distribution is actually in both directions. So in our course, we are limited ourselves into one-way slab design, okay? One-way slab, all right? So that's where we're at. Now, to give you a little bit more insight from the 3D view that you see that there are two directions for the reinforcement. One is longitudinal, as you see that, and the other is transverse. And like I said, in the longitudinal direction, we consider the bending moment to actually calculate the design for the reinforcement. But for the other direction, we usually use the code requirement, which we'll talk about today, okay? Which we'll talk about today. All right, so from here, we move on, right? We quickly went through this calculation for longitudinal span, right? First thing, we have these. So the examples here, we have a one-way slab that we have both the dead load, that is the uniformly distributed dead load, and also the live load, which is also uniformly distributed live load. All right, so in this case, coincidentally, we have the identical values for both the live load and dead load. Both of them are 150 pounds per square foot. Now the concrete is 4 KSI, pretty regular concrete. And one thing I want you to keep in mind that, and this, if you pay attention in exam, that the yield strength for the one-way slab is always lower than the longitudinal reinforcement for the beams. Usually for the beams, we're talking about 60, 75 KSI, but for one-way slab, usually 40 KSI. Okay, so that's something you should remember. All right, so moving forward, and first thing you do is that you have to estimate the height of the slab. So for that, we just have a constant equation right here at 1/20 inches, multiplied by this coefficient. Inside is a 0.4, which is the constant. Add on the value, which is 40,000 PSI divided by 10,000 PSI. give you a number here, okay? And I think that this number is 4, 1, 2, 3, 4, 1, 2, 3, 4. I think there's a 0 missing right here at the bottom, okay? I think so. Give me 1 second. This should be 0.4 and this should be 0.4. So it's got to be 0 missing right here. Okay, so if you really don't like the so many zeros, you can write down the 40 KSI divided by 100 KSI. Okay, so that is the ratio. So you should get a 0.8. Okay, you should get a 0.8 out of this two. Okay, so with that, you can get the height of the slab from 4.8 inches, round it up to 5 inches, and we want to estimate the depth of it. And you have the concrete cover in this case, which we said is 0.75 inch for the concrete cover. And again, this is for interior exposure inside of the garage, right? If it's for exterior, things are different. Now, with that, we can get a depth which is 4 inches. If you don't know all these specifics, right? You don't know the specifics, and you want to still estimate the depth of the slab, you use 95% as a constant multiplier in front of the height, 95%, okay, 0.95 to get the thickness and depth. All right, now once we have thickness and depth, we first trying to design for the longitudinal direction of reinforcement. And to do that, we have to first get a moment, okay? And that moment comes from the dead load and live load combined. And the dead load comes from the density multiplied by the cross-section area. And from last lecture, I keep emphasizing when you calculate the cross-section area, of course, one dimension is the slab thickness, which is 5 inch, but the other dimension should be the unit strip, unit strip. The concept of unit strip is that when you design for the longitudinal direction, you only consider 1 foot of the cross-section, 1 foot of the cross-section, and that's what it is, right? This 12 inch, that's what it is. Okay, so from there you get a dead load, and then you similarly do the live load. And again, for the live load, it's just a 1 foot because it's a unit strip again. Once you have the dead, you have the live, you have the applied load from 1.2 dead plus 1.6 live, and you get the ultimate load, which is the factored loading, right? And everything is in terms uniformly distributed, So mu, which is the bending moment, equal to omega u L squared over 8, and L, and this is L, and this L here is the shorter span, which is a 10 foot. Don't forget, okay, 10 feet. And from there, you get your moment. And one thing I want you to keep in mind that this is a little bit different from the beam design. Once you have the moment, things we're doing the unit strip. So automatically you put a per foot at the end of it. You put a per foot at the end of it, showing that this is for the unit strip. All right. And once you have that, you have the bending moment, right? And then you have the bending moment, you can follow the beam design, right? We talked about this in the previous chapter, how you design for flexure members, right? And you go ahead, estimate the area required first and provide some bars, right? And then go back to do this A, effective compressive size A. And then finally you arrive at a certain number for the required reinforcement. And keep in mind here, right? This is again inch square per foot. And when I were to provide the bars, I have to convert the bars into a requirement like this. So how do I do the conversion? I have to use this area multiplied by 12 inch over the spacing S. Okay, and the rationale is that I do not provide bars per unit strip when I do construction. I provide bars with certain spacing that can be converted into a per area or per unit strip, right? So once I do that conversion, I realize that, okay, all I need is the 6 inch spacing for a number 4 bars. And again, folks, when you design for one-way slab, either is going to be number 4 or number 3. And number 3 is pretty unusual, so number 4 is most likely the bar of the choice, okay? And you go with number 4 with a 6 inch spacing, and voila, you fulfill your requirement. And once you have that, you bring the reinforcement back into the cross-section and do analysis, right? To make sure that applied moment is smaller than the design moment, which is 4.56 kip foot per foot, okay? I cannot emphasize this enough, all right? It's per foot. In exam, if you forgot to write per foot, you will lose 2 points, okay? You will lose 2 points, all right? Okay, I hope this is clear. Any questions about this? Anything, folks? Any question about this? Anything? Okay, well, if I haven't put you in sleep yet, Wednesday only, right? Let's continue, right? Let's continue. This is how we design for one-way slab. one-way slab. All right, so this is a flexure reinforcement, right? This is a flexure reinforcement, but keep in mind that ACI always have a minimum requirement. So ACI specifies, zoom in, a minimum reinforcement requirement, okay? Minimum reinforcement requirement. Okay, that means that, okay, although we have provided reinforcement, right? What is our provision? Our design is number 4 bars at 6 inch, okay? And convert that into a area per foot, right? Convert that area to per foot, and that is 0.4 inch square per foot, right? How do I get that number? Number 4 bar cross-section area, 0.2 inch square. Per foot, I have 6 inch, so per foot I have 2 bars, so I get 0.4 inch squared per foot. That is provided. And from ACI, actually says there's another minimum requirement, okay? There's another minimum requirement. So from ACI, it's actually in the ACI R. So from ACI comments, ACI revision, okay? That the minimum requirement, AS minimum, is actually 0.002 AG. Okay, now in this equation, 0.02 is a coefficient, nothing said about it, right? It's just a constant. AG is actually the cross-section area. That means that it is 0.002 multiplied by the height of the slab, which is HF, and multiplied by the unit strip, right? Unit strip, in this case, is 12 inch. Okay, so from there, I can do the calculation, which is 0.002 multiply HF, the thickness is 5 inch, and multiply 12 inch, and I get this number to be at a 0.12 inch squared per foot. Okay, and let me just move this a little bit left so we see it better. Okay, all right, so that is a requirement, and apparently what we provided, right? AS per foot provided, right? POV, right? Provided, sorry, equal to a 0.4 inch squared per foot, which is much larger than the minimum requirement, that is 0.12 inch square per foot. So we're okay. All right. So in this case, we're okay, meaning that we satisfy the minimum reinforcement requirement from ACI. And at this point, we say that, okay, we're done with longitudinal direction and the selected design to be number 4 bars at 6 inches. Okay. So that is all we have to do for the bending, right? You think of it, this is for the bending moment, all right? And now let's take a look at the transfers. Let's take a look at the transfers, all right? What are the transfers? What are the transfers, right? So the transverse reinforcement says that, before, let me think, before we go to transfer, okay. So before we go to transverse reinforcement, I forgot one thing, and let me just, and in addition to ACI minimum reinforcement requirement, there are also other spacing requirement provided in ACI, okay? Spacing requirement. Okay, and don't worry, at the end of the example, I'll list a table to help you understand this, okay? But as we're solving the problem right now, let's check this minimum reinforcement and also spacing requirement. Now, if we say reinforcement, we say minimum, but for spacing requirement, we have to say S max, the maximum spacing, okay? Now, the maximum spacing per ACI has to be, and again, this is an ACR revision, okay? ACR revision, it's not in the 318, so you might just want to write down these equations. You might just want to write down these equations. Let me just list this two, one here and one here. So you need to keep this in your crib sheet. And then S max has to be smaller than the following, right? What are the following? 3 times of the slab thickness, that is 15 inches, okay? And another constant, which is 18 inches. All right, now these two numbers, right? These two numbers, and I say 15 because we have 15, right? We have 5 inches of slab thickness here, right? But in other cases, you have to do the number, right? And this in ACI is called deflection control. Deflection control, meaning I don't want to have my reinforcement to be so scarce that the rigidity of the slab is too low, I have a lot of deflections. So these two numbers are deflection control, okay? And then let's do this equal to the maximum, equal to the minimum of these following, okay? And the other one is 15, it's a constant, multiply 40,000 divided by Fs, okay? And then minus the 2.5 concrete cover CC. Okay, and you say, what is Fs, right? Fs is 2/3 of the yield strength for the bar, and CC is just the concrete cover. Okay, concrete cover. Okay, all right. Now, just for us, for this case, right? 15 multiply 40,000 and divided by 2/3, right? So 2/3 of 40,000. And these 40,000 cancel each other. This becomes 1.5. Anyway, minus 2.5 multiplied by concrete cover. Here we provided 3/4 concrete cover, and this number ends up to be 20.6 inches. Okay, 20.6 inches. And the other number right here is 12 multiplied by 40,000, 12 multiplied by 40,000 divided by Fs, and then that is 18 inches. Okay, that is 18 inches. So out of these two equations, ACI call it crack control. Okay, let me use the same bracket so be consistent. And this is called crack control. Now, what does crack control mean? Crack control means that I want to have a minimum amount of reinforcement or maximum spacing, and then that will satisfy the limitation of the crack. So the concrete won't crack. Okay, the concrete won't crack. So that is all the limitation you have for the spacing. Let me just make this more closed. All right. So let's just do a simple check. The reason why I neglect in the first place, because usually these requirements are not the last constraint you want to see. Usually it's the bending moment dominance. Okay, so these are the least concern you have in most of the cases. But let's just take a look at the number, right? 15, 18, 20.6, 18. Out of them, 15 is the smallest number, right? So this governs. All right. And even this governs our provided reinforcement spacing at 6 inch. And that is much, much lower than the 15 inches. So in our case, okay. Okay, in our case, okay. Okay. And now, forgive me, I said earlier, a little bit too earlier, just now, that this concludes the longitudinal reinforcement. So I will just put here this concludes longitudinal direction design. Okay, so pretty much at this point you have enough bars for your bending direction. That is number 4, size number 4, and at 6 inches. Okay, so it's not too bad. All right, not too bad. Now, after we do the longitudinal direction, let's try to do the transverse direction. So transverse direction, right? Now, you know that since I'm doing the one-way slab, means that I only have moment in the longitudinal direction. That means that in the transverse direction, I don't have any bending moment. So if I don't have any bending moment, I need to put reinforcement in it. The two things I need to consider are the shrinkage and temperature. Now, these are the two elements I need to consider. Okay, so how do I consider shrinkage and temperature? Matter of fact, shrinkage and temperature is actually easier control because all I have to do is satisfy the following requirement. So for shrinkage and temperature as max, well, let me try the AS min first. AS min, minimum reinforcement, is the same as before, and that is 0.002 B, or let's use AG, which is the cross section, right? AG is the cross section area, which is 0.0, wait a second, let me see here, 0.02 multiplied by 12 inch, that is the width of it, and then height 5 inches, so 0.12 inch squared per foot. See here, 0.12 inch square per foot. Good. Okay. And this is our first requirement. And then second requirement, S max. Okay. Second requirement, S max. Now for transverse, okay, only care about crack control. Only care about crack control. So for transverse, things a little bit different from longitudinal, okay? Only two equations you have to worry about. One is 40,000 divided by Fs minus 2.5 cc concrete cover. And that number we calculated before, 20.6 inch. And the other is 40,000 divided by Fs. And that, ladies and gentlemen, is 18 inch. And out of them two, you know that this 18 inch governs, this 18 inch governs. Okay. All right. Now, for this is only the transfer direction, right? You have a 18 inch and you have a 0.12 inch squared. And then we're going to use number 4 bars, right? So how do I do the design? I am going to do number 4 bars. So I know number 4 bars and I have to provide the spacing. So let's just try the 18 inches, shall we? Because out of the 20.6 inch and 18 is smaller, right? So let's try that. But I also need to satisfy this requirement, which is 0.12 inch square per foot. So how do I do that? I convert this to be the provided, right? So AS per foot provided equal to 0.2 inch squared per 18 inches, right? That is per what foot? 1 point, so 18 divided by 12 foot. Is that right? 18 divided by 12 foot. Okay, I need a little bit help here. So let's just pull out your calculators and start getting the number from this one. So 0.2 and divided by 18. So let me just do 3, 2. So that is 0.2 multiplied by 1.5, right? Divided by 1.5. Is that right? Divided by 1.5. Okay, so roughly I'm looking at 0.2 multiplied by 2/3. Right, so that is 0.1. What is it? 0.4 divided by 3. So 0.1 and 3. Is that right? 3 and 3 inch squared per foot. I neglect the unit. Okay, carry the unit all the way through. Okay, so that is how much I provided. So check this number, and I realize that this number is indeed bigger than the requirement. What is the requirement? Requirement is 0.12 inch square per foot, isn't it? So I'm okay. Okay. Now at this point, I say, look, for the transverse reinforcement, it's simple. I am going to use the number 4 bars at 18 inches. And I'm done. Okay. So you see, it's not hard at all, right? It's pretty simple for the transverse direction. And you may ask, say, Bob, why are you using number 4 bar size? Can you use others? Sure, I can, but it's just a lot easier to use the same bar for both directions, right? And the other direction is number 4 with 6 inches, and this direction number 4 with 18 inches. So after everything said and done, I just want to visualize what I end up having, right? What I end up having. So I pull the slab up and draw it like that. This is my slab. And again, let me try to draw it carefully. This is my slab, and I know that 1 is the shorter direction. So when you do drawings, let me make sure that you tell people this is 10 foot, the shorter span, and the other span is the longer span, which is 25 foot, right? And there are 2 directions, right? So let me just use 2 colors. One is longitudinal reinforcement, use the red because that's bending. So that one sits right here, right? And another 6 inch right here, 6 inch right here, okay? And that is at the lower side of the slab, right? So you have that 6 inch apart, 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 okay? So this red fellow here is number 4 at 6 inch, get it? Number 4 at 6 inch. Okay, now the other direction is the transverse direction. So that one goes this way, okay? And you notice that this is not proportional because this is much more spaced out, And that, ladies and gentlemen, is number 4 at 18 inch. And to be precise, I want to put this one to be, sorry, wrong color. to be this one to be transverse direction, transverse, and this will be the longitudinal direction. And then we're done. Okay, then we're done. All right, so now that is the one-way slab design. Okay, not so bad, isn't it? Not so bad. Okay, all right, any questions? Any questions for me? Anything else? Okay, all right, so we are done with one-way slab, okay, one-way slab. And in the exam, you will see one example probably in the one-way slab design, and that probably in the first question, and that is the multiple choice and fill in the blank problem. I most likely will not have a full workout problem for one-way slab because it's just trivial. It's not that challenging, okay? We'll save the space for other problems, okay? Now with that, we're able to design one-way slab. It's a little bit long, but bearable, right? So we can do a slab, make sure that the ratio satisfies 2-to-1 ratio. And for that one, we only consider bending moment in one direction and ignore the bending in the other direction, and put both reinforcement, one for bending and the other for shrinkage at temperature, and conclude the design process. Okay, and then the question comes is that, okay, Bob, now I know how to do the one-way slab, and this is on the simply supported. This is on the simply supported case, right? So simply supported case, meaning if I have a slab that going through this supported case, which means I have a slab, right? And I have a nice cross section like that, and I have simply supported conditions, I end up with a bending moment of 1/8, right? Remember this, 1/8 omega UL squared, omega UL squared. That is easy to calculate, isn't it? To get the moment and do the design, right? But in reality, all your slab are not necessarily simply supported. All your slab actually continuous. Means that I usually don't have a one simply supported slab, just simple like that, right? And usually you actually have a poured monolithic slab, means that you're most likely going to have a slab like this, and you will have a beams poured together like that. Beams poured together like that. And sometimes the beams are not uniformly spaced, isn't it? And that will be the continuous slab, right? So for the continuous slab, you know that, right? It's have a uniformly distributed load on top of it, similarly as in a one-way slab. But the bending moment seems to be different. Why so, right? I'm just gonna save my time now, draw all of them. But the bending moment seems like, okay, I might have a supported condition that maybe at the end of it still simply support condition, but in the middle, right? In the middle, I may have rollers underneath it. So these are continuously supported, right? And now I have loadings. Sometimes I have all this uniform loading, right? Uniform loading on top of it, okay? And I can do this dead load and find out the bending moment, fine, cool. But what if I have live load here? And I have live load here. I have live load all over the place, right? And the question is, which pattern gave us the maximum bending moment at each beam? Which pattern gave us the maximum bending moment at each beam? You say, Bob, you're confusing me. What do you mean by beam, slab? What are you talking about, right? I'm a little bit confused. Well, you look at this, right? So we're talking one-way slab, still one-way slab, okay? But now the slab we're talking about, this is the strip. This is the 1 foot strip. So similar here, we have a one-way strip, one-way slab and unit strip like that, right? This is 1 foot. But you notice that the bending moment at different locations, all right? When I say different locations, bending moment here, here, and at the end of it, 0, right? So at the end of it, 0, right? That's no bending moment. But in the middle of it, they are different. They're different. Hence, you cannot treat it as the uniformly distributed load where you have the maximum bending moment in the middle of the span, you're happy and be done with. You actually have to find out the bending moment along the span. You have to find out the bending moment along the span and also at the support to figure out where you have the maximum bending moment and then design the slab for it. then to design the slab for it. But the problem I have is that, okay, say if I have a uniformly distributed load, right, like this, and I draw the structure diagram, the moment diagram shows me like this, right? So I have a positive bending moment and then have a, oh, sorry, I have a positive bending moment in the middle span, and then have a negative bending moment, and then positive and negative and positive and negative and positive and maybe a zero, right? So these are my moment diagram, just say moment diagram, okay? Moment diagram, okay? And now when I put the red loading, right? Red loading on top of it, that means I'm going to change my moment. So first thing, when I put this, I amplify my positive bending moment, isn't it? Because I put the moment here, I put load here, right? But at the same time, I will have to reduce the negative bending moment. I have to reduce the negative bending moment, right? So it depends how it goes, right? I may have to alter my bending moment diagram. I may have to alter my bending moment diagram. Okay, I'm just making things up, okay? I haven't done a calculation, but I'm just drawing by hunch, right? So the change will maybe affect your maximum bending moment in the middle span, but reduce your negative bending moment at the support. So that means the location of maximum bending moment, or how much moment at each section, we're talking about either at the support here, this is easy, right? The zero, but in the positive bending section, negative section, positive section, negative section, positive section, negative, positive. And all these sections, it's not constant. All right. This is a bit confusing, but let me say this. The moment along the span is not constant, and they're changing. They're changing. Depends on the live load pattern or dead load pattern you are citing on the slab. So what does it mean, Bob? What are you trying to say? I'm trying to say is that if you really want to design the slab at different locations for the moment that exerted on this location, you have to run a sophisticated structure analysis to get the moment distribution in the slab first, and then design for it. And that is too complicated. That is too complicated, and that's too much time needed. All right. So in this case, we don't do that. We don't do that. And for the first time in my lecture, probably the only time, I'm going to use the PowerPoint, okay? Because I have some table embedded in the previous lecture's note I want to share with you, okay? So I'm going to stop sharing and go back to the PDF file, okay? Just give me a second here. And look, this is from last time I wrote, okay? And there's too much writing, and also I have a table following up. You can see it better, and I'll upload this, by the way. And this is what I'm talking about. When you have different patterns of loading, your moment changes, your maximum bending moment changes as well. So realizing that, ACI says, when you design, you have to consider this pattern loading, meaning there got to be certain pattern give you the worst moment distribution. So ACI pretty much defines this pattern. So, okay, look, you have to consider the following pattern, and you don't have to run calculations. I will provide you a table to do that. All right, so this is ACI design criterion. So pattern loading, to achieve the maximum bending moment at critical sections, at all these sections, ACI says, I define a loading pattern and to determine this. And this is both for moment and shear in a continuous beams and one-way slab. The key word is continuous, okay? I cannot emphasize continuous, all right? Continuous means annotate here. Continuous, make sure you know this, okay? Has to be continuous, means that I have to have a slab or beam going across the support, slab or beams going across the support. All right, so what patterns, Bob? Oh, these are patterns. First pattern, factor dead load on all spans, plus factor live load on two adjacent spans, no other. What does it mean? It means that if I consider B, section B here, of course, section B is just the support. So actually I have two sections, B minus or B left or B right, right? Section on the left of the B or section on the right of the B, right? To consider this, and that is the maximum negative moment, I need to apply factor dead load on all spans. And then plus the live load, which is 1.6 live load on the adjacent spans, on these two spans, to get the maximum bending moment. All right. But if I want to find out the bending moment here in the middle span, okay, in the middle span, what I do is different. I also have to do the factor dead load on all spans, and add on the live load, factor live load on the alternate spans, on different spans. All right. So these cases actually have to be considered, which means you supposed to do this pattern loading with your factor loading and come up with a structure analysis, get a bending moment, and use that bending moment to design reinforcement. However, it says, look, I have a cheat sheet. Means that I did it myself, okay? And I consider all these design patterns and find out the moment. Find out the moment at different cross section and eventually give you a table. And ladies and gentlemen, please put on your note that figure 1210. This is the figure you need for your creep sheet. And these are the calculated coefficient. Okay, so how to use this table, right? First, let's read this table. Let me zoom in here so hopefully you can see better. Do you guys see this clearly? Anyone? Are you sleeping? You guys see this?
Yes, I can see it.
We can see it.
Thank you, and apologize. Today has to be a PowerPoint. Okay, I hate that, but I just have to, with all this information, it's easier this way. So you take a look at this, right? So we have a continuously supported slab. And now we have column, right? Column, but you know, they are actually support, right? They're actually support. And this is poured monolithically together, poured together. All right. So how to read this table? How to read this table? Now I write something on top of it. I wrote something on top of it. Okay. So actually it can be divided into three rows. Now this red one here, first row is called discontinuous and unrestrained. Now, I'm pretty sure you have read this word, understood these words better than I did, but you look at it, you don't understand, right? What do you mean by discontinuous and unrestrained? What do you mean by that? I draw a little figure for you, okay? Now, see this one here? Discontinuous and unrestrained. Discontinuous end meaning it's on the end of the structure, meaning no more, nothing. This is end of it, no more structures. Cliff, you're gonna fall out, okay? This is end of it. And unrestrained, meaning simply supported, meaning they're not poured together. There might be a supporter. Remember the bridge thing I was talking about? There might be a neoprene pads between the beam and the column. Similar like that, right? They're just simply supported. They're not poured together, cast together, okay? Meaning free to rotate. Free to rotate, no moment translated from the beam or slab into the column or vice versa, right? No moment translation between the members. So that means unrestrained, free to rotate, okay? This is called scenario one, meaning if you have end condition like this, you're going to follow the first row of the numbers. What are these numbers? Minus 0, meaning 0, right? Because it's free to rotate, there's no moment, right? So I know that a moment at this cross section is 0. And then at the first span, middle span, I have a positive 1/11, and you say just a number, positive 1/11, what? Positive 1/11 multiplied by omega u ln squared, okay? Omega u ln, omega u is the factor load, okay? Ln is the span here. You can see that Ln is span here for this particular span, and that is the clear span, meaning from the interior face of the column or the support to the interior face of another support, and that is the span length. All right, and then at the right hand side of it, and you have a negative bending moment. Okay, be careful. I put the sign in front of it, so you should know. Okay, negative bending moment 1/10 on the left side of the support, and then going across, there's a negative 11, and then positive 16s, negative 11, and negative 11, and so on and so forth. You say, Bob, what do you mean so on and so forth? Notice, right? Only the left span is 0, 1/11, negative 10. The rest of them will always be negative 11, positive 16, negative 11. This is negative 11, positive 16, negative 11, negative 11, positive 16, negative 11. Do I need to go on? I don't, right? You know the rest, right? Just repeating this span. So this is called scenario number 1, okay? It's called discontinuous and unrestrained, meaning free to rotate, You use this row of numbers, okay? And don't forget, each number has to be multiplied in front of this omega u ln squared, and that is the moment at each location, okay? Moment at each location. All right, so that's the first row. Now, second row, we call it spandrel, right? Spandrel meaning I have the support poured together with the beam, but just at the bottom part of it, not the top. It's not a column straight out, extending out, and just have a end frame like a joint, okay? If you have this condition at the end of it, you follow the middle row where is a -1/24. Be careful, it's not 0 anymore, right? I have moment constraint. So there's a number and +1/14, -10, -11th, and +16, -11th, -11th, and so on and so forth, right? Repeating the span, right? This span. Okay, so that is for span joint. And last but not least, for the column, we have a column and beam or slab joint here. You have -16, +14, -10, so on and so forth, like that. Okay. All right. So this is when you have more than 2 spans. Do you see this red writing? More than 2 spans. Okay. I have 1, 2, 3, 4, 5, so many spans, more than 2 spans. I use this figure. Okay, and you see here, I have 1/10 bigger than 1/11. You say, Bob, I know that. I learned that from elementary school. Yes, I know. The reason I write down here is take a look at the joint here. Take a look at the joint here. When you have a -10, -11, they are different, isn't it? They're different, isn't it? But when you design for the reinforcement, this reinforcement probably going to stick throughout. The reinforcement is going to elongate or continue or extend throughout. That means that you're only designing the reinforcement for one number. It's easier that way, right? So which number? You pick the larger number, right? Value-wise, right? Not the sign, but value-wise. So 1/10 is bigger than 1/11. So when you do design, you usually pick this number, okay? Although they're different. So in the exam, when they ask you to calculate moment, you use these numbers differently. But when you do design, you pick the larger number, okay? Now I put a star on this, meaning this is the only thing you need to remember and only thing you need to know how to use, okay? And this is for more than 2 spans. Now, for 2 spans, right? I have another figure here. You use this figure instead, okay? You use this figure instead, okay? All right, now I did not fill up the blanks, which means there are some empty points, right? When they are empty, 1/9, right? Meaning they're all 1/9s, okay? So 2 spans, you use this figure, okay? Now, when your slabs with span that is less than 10 feet, you use this figure, okay? And when you have a column stiffness 8 times higher than beams, and this is really, we call it strong column, weak beam condition, meaning you have a very huge column section, the beam is pretty slender. In this case, you use these figures, okay? And I have a whole lot of reason for that, but for our purpose, you don't have to know that. If you're interested, I can tell you more about it. Basically, it's a moment distribution thing. But these are all the tables you need to use. And quite frankly, you're probably going to end up using the top one and the second one, these two, okay? These two. By the way, you guys see my mouse cursor? When I move the mouse cursor, you guys see it? Do you guys? Thank you. Thank you. So just these 2 figures most likely going to be used, okay? These 2 at the bottom here, sometimes you need, sometimes you don't, okay? All right. So with that, these are the nice tables or figures you need to use. I keep showing you this, right? Meaning you have to put this in the creep sheet. Now, I know this is heavily annotated, heavily modified and whatnot, but please redraw it. When you redraw, you understand. If you don't send me an email question, I can answer that, right? So please redraw this, right? This is what you need to have in creep sheet to solve the problems for homework and for exams, okay? All right, so surely that's nice to know, right? And we call this ACI moment coefficients, right? It's just some indexes and numbers ACI provide us, so you don't have to run through the whole complex structure analysis to do the moment, right? To get the moments. Okay, so it's surely easy to use, and I like using that a lot, but be careful. There are limitations. Okay, which means there are boundaries, right? Criterions that you have to work with to be able to use this table, to be able to apply this table. First thing, it has to be 2 or more spans. Meaning if you have span like less than 2, single span, simple span, you cannot use it, right? And second, span lengths are approximately equal, with longer of the 2 adjacent span not 20% greater than shorter, meaning that, yeah, you have multiple spans and each span should be approximately same to each other. And the difference should not exceed 20%. The differences should not exceed 20%. And that is very important, okay? So if your difference exceeds 20%, you cannot use this table anymore. You cannot use this table anymore, all right? And then third, uniformly distribute. If you have a concentrated loading, forget about it. You cannot use the table, all right? Number four, the live load does not exceed 3 times the dead load. Unfactored, okay? This is before you do 1.2, 1.6 business. The live load has to be smaller than 3 times the dead load. All right. Number five, prismatic members. Everything has to be square. Okay. You have a square column. You have a not square. You have the rectangular section of the column, rectangular section of the slide. Everything has to be rectangular, right? Why? Because all this were actually calculated based on the torsion resistance of the rectangular section. If you have a circular section, you cannot use this. Okay. Be careful. And number six, if 1.4 times the dead load is greater than 1.2 plus 1.6, you cannot use this coefficient. You cannot use this coefficient. Okay, so you have to check. You see, so all these 1, 2, 3, 4, 5, 6 criteria has to be satisfied before you start thinking about using the table. Okay, before you start thinking about using the table. So you have to respect the rules. You say, Bob, all these are rules. Can we bend it? Sure, you can. You're building collapses. Okay, you're building collapses, so be careful. You have to obey these rules. All right. Okay, with that, we're done with the concept of this one-way slab. We're going to do a one-way slab moment coefficient example, which is here on tomorrow. Okay, on tomorrow, and I will talk about some of the exam problems on shear and all the other things tomorrow as well. And if you have any other questions, please stay behind and we can discuss them freely. Okay. Other than that, I will see you tomorrow. Tomorrow, 1 o'clock. Okay, don't be late. Online again, 1 o'clock. Thank you. Bye.
Bob,
Yep.
is this figure on Canvas?
I mean this one, right? I will upload like right now.
Okay. And can you go back down to the number 6 rule?
Oh yeah. Hold on. Yeah, right here.
Okay, thank you.
Yeah, I'll upload this online right now, so you will have it.